Today we will discuss how to design timber beams. The design procedure is done based on IS 883-1994 as per clause 7.5 procedure with the help of a set of problems. The first problem, it is given that a deodar timber beam carries a UD load of 16 kN per meter, including its self-weight, and it is having a span of 5 meter, and the beam is simply supported at its ends. It is asked to design the beam. So first of all, we will be writing down the properties of the beam as well as the end conditions given. So the beam is a simply supported beam. UD load is 16 kN per meter. The span of the beam is 5 meter. The end bearings are not given in the question. You can assume a suitable end bearing width. Let us assume it is 300 millimeter bearing width, and thus the L effective becomes the span plus the bearing width, that is 5.3 meter. It is given that deodar timber is used. The deodar timber properties can be taken from table 183. So this is IS 883 1994 design of structural timber in building. So we have to move to the table 1 where deodar timber is listed. Here you can see deodar and all different properties of timber is listed here. The properties that we need are modulus of elasticity as well as permissible stress values. Modulus of elasticity of deodar wood is 90.8 into U per mm square. Okay, and a set of permissible stresses, we need bending stress value, then shear stress value, and compression perpendicular to the grain. Bending stress value is given in 3 different types: inside, outside, and wet location. If nothing is specified, you can select one among them. For this particular problem, we will be considering inside location. So for deodar wood, for the inside location, 10.2 is the stress value. The shear stress value is 0.7 Newton per mm square, and compression perpendicular to the grain is required for the bearing and 2.7 Newton per mm square. So all those values can be just written down for future references. Now we shall move on to the design procedure. The design procedure is like, first of all, we have to calculate the maximum bending moment and maximum shear force based on the type of the beam and its end condition. So maximum bending moment for a simply supported beam with UD load is WL square by 8. W is 16 and effective is 5.3. Hence the maximum bending moment becomes 56.18. Similarly, maximum shear force is WL by 2 for simply supported beam with UD load, and we get the value of shear force as 42.4 kilonewton. Once the maximum bending moment and shear force are calculated, now we have to assume suitable cross-sectional dimensions of the beam. For that, a thumb rule is given in IS code, clause 7.5.5 and clause 7.5.6. So we have to move to the 7.5 clause, which will be entirely for the design of flexural members or the beam members. So 7.5.5 gives an idea about how to start with the width of the beam, and 7.5.6 about depth. Regarding the width, it is said that the minimum width of the beam or any flexural member shall not be less than 50 mm or L by 50, whichever is greater. So we have to calculate L by 50 first. So here we can see 50 mm or L by 3 meters or 5300 millimeter. So the L by 50 value is 106. We have to take the greater of 50 and 106, and we have to assume a suitable width based on the condition. It should be greater than 106. So I am assuming here 110 as the width of the beam. And regarding the depth of the beam, the criteria is it shall not be taken more than 3 times the width. So we have the width 110, 3 times the width is 330. the depth more 30, that means depth is 300 mm. So I am proceeding with the breadth of 110 and depth of 300 for the particular condition of beam. Now we have a set of checking has to be done in order to ensure that the beam satisfies the conditions of bending, shear, deflection and bearing. Okay, so first of all we shall do the for bending. Here check for bending is provided in clause 7.5.4, and before that we can just calculate what is the maximum bending stress coming onto the structure due to the bending moment. For that we will be using the bending equation m by I is equal to F by Y. So the bending stress F is equal to m divided by I by Y. I by Y is the modulus. Section here moment value already calculated as 56.18, and the section modulus Z is equal to I by Y. I is BD cube by 12 and Y is D by 2. Therefore Z is BD square by 6. Now the bending stress can be calculated as M by Z, and that is 34.05. As per clause 7.5.4 of 883, we have a clause that the bending stress has to be multiplied with a constant K8. So I have the equation for K8. It is given in 7.5.4. For the rectangular section, K8 is 0.81 d square plus 89400 divided by d square plus 55000. So calculate the value of K8 with capital D as 300, and it is obtained as 1, and thus the bending stress value is K8 into 34.05. The calculated M by Z value must be less than FB, that is the allowable bending stress, as per table 1. It is given in clause 7.53. Here you can be less than FB, which is the bending strength for the particular deodar wood that is available in table 1 of in which the properties of deodar wood is listed. We can just go back and see what is the bending strength or bending stress, maximum permissible bending stress value. As we have seen earlier, here you can see the bending stress value is 10.2. Okay, so 10.2. So the evaluated is 34.05, and the FP value, allowable strength value is 10.2. Okay, so our M by Z value should not be greater than FP, but here you can see M by Z is greater than FP, that is 34 is greater than 10.2. So we have to redesign the assumed structure. So I'm redesigning it. B is assumed to be 200. I have increased B and D to 200 mm and 500 mm, and recalculating M by Z, I got the value, and new value of K8 is calculated using D is 500, and F is equal to K8 into new M by Z value, and thus I got the bending stress as 9.18, which is less than the allowable value 10.4. Okay, hence the structure becomes safe. So the new cross section is 200 mm width and 500 mm depth. Next I am moving on to check for shear. In check for shear, the to calculate is H is equal to VQ by IB, which is specified in clause 7.5.7. Okay, we shall just move to 7.5, 7.5.7.1. Okay. Here you can see 7.5.7.1, and the equation for bending, shear stresses BQ by IB, where Q is half of B into D by 4. I value BQ by 12. I'm calculating H is equal to V value is the shear force value. We have already calculated at the beginning as 42.4 kilonewton. Then Q is half of B into D by 4. So what happens? Q value 6.25 into 10 raised to 6. Now the I value is BD cube by 12, that is 200 into 500 cube by 12, and B value is 200. Thus I got H value as 0.637. Now I have to check whether this is less than the allowable value. The allowable value can be obtained from table 1 for the deodar wood. So I am going back to table 1 for the deodar wood. The allowable shear value. Here you can see for deodar wood it is 0.7 and our value of H is 0.637 and hence it is safe. Now moving on to the check for deflection. There is an allowable deflection as per 7.5.9.1. Okay, we choose 7.5. 7.5.9.1. Here you can see the allowable deflection. Here it is for frictional members L by 240. Okay, so L by 240 is 5300 by 240, that is 22 mm of deflection is allowed. Now let us check how much is the deflection coming onto the given structure. For a simply supported beam, maximum deflection equation is 5 for W is 4. W is 16 kilonewton per meter. I have to convert it into Newton and millimeter. 16 kilonewton per meter when converted to Newton per mm. Again, it is 16 into 1000 divided by 1000. So it remains as 16. Then L value is 5.3 meters. Then E value from table 1 is 94.8 into 100. I is BD cube by 12 we have already calculated. So I get it as 8.32 mm. Allowable one is 22.03 and hence. Now we to check for bearing. The allowable bearing stress as per clause 7.5.8.3.1. It is given that in table 1 allowable bearing stress is given. So you can go back. You can go back and say in page number for table 11 for deodar wood, you can here's their strength values obtained as compression perpendicular to the grain. So the value here you can see it is 2.7. So perpendicular to the grain, table 1, the value is 2.7 and allowable value is 2.7. The bearing stress value can be obtained using the equation V by BD. V is the shear force value 42.4 kilonewton and B and D. Here you can see the beam resting on the column, the figure. B is half the width of the bearing. I have assumed width of the bearing in the beginning. So 300 mm is the width of the bearing. Half of that is considered as B, that is 150. 150 and depth is the breadth of the beam, that is 200 I have assumed. Thus I get the bearing stress as 1.43, which is less than 2.7, which is the allowable value and hence safe. So that is all about designing a timber beam in which we have to assume the cross-sectional dimensions. We have to calculate the maximum bending moment and shear force as per the beam conditions. And then we have to do the check shear deficient bearing. Okay. Now let us discuss a few questions that is asked for the university. Almost all the questions are similar to the one we have discussed. Second question, which is having a slight different type of input value, is design a beam of clear span 4 meter and spacing 2 meter center to center in a residential building with bearing 250 and dead load 1.5 kilonewton per meter square and live load 3 kilonewton per meter square. What happens is we center to center distance is 2 meter. So what happens for a single beam? Half the load is coming from one side and half the load from the other side, and the total load which is acting as 2 meter width. We need the load in kilonewton per meter. Here the dead load and live load are given as kilonewton per meter square. So in order to convert it into kilonewton per meter, we have to multiply it with the distribution of load coming from both the sides of the beam. So that means dead load plus live load, that is 1.5 plus to standard distance between the beams. Okay, then span is given to be 4 meter, bearing width is given as 250, and thus the L effective value is 4.25. The wood type is same as previous case, that is deodar. All the properties can be obtained from table 1. The procedure remaining is very similar. Bending moment and shear force are calculated with the values of W9 and L 4.25. Then assuming the dimensions. Here B minimum is obtained as 85. Assumed 150 place, we had to redesign. So I'm keeping the width of the beam as 150 and depth of the beam as 400, because 3 times 150 is 450. I have to decide the depth of the beam lesser than 450, that is I am keeping it as 400. Now I have 4 different checks. Check for bending, where I have to calculate bending stress and compare with the FP value from table 1. Here MBZ I got as 4.77 and the bending stress or bending strength from table 1 is 10.4, and hence then for calculate H equal to VQ by IB, which I obtained as 0.478, and it has to be compared with the maximum stress strength value, that is 0.7. 0.7478 is less than 0.7 and hence safe. Then check for deflection. L by 240 is the allowable deflection, that is 17 mm, and the maximum deflection value is 5 by 384 WL raised to 4 by EI, which is 5 mm, which is less 17.7. Check for bearing. Allowable bearing value 2.7 we already knew. We have to calculate the bearing stress V by VD, which is obtained to be 1.08, which is less than 2.7, hence safe. So the procedure is almost the same. There may be slight variations. You have to identify the variations and do. In the third question, it is 3 meter span, 1.5 meter is the center to center distance, 2 kilonewton and 2.5 kilonewton are the dead and live load, and that is the difference. So I have to get the properties of teak wood from table 1. So I can just move down. I can just move down and find where the teak wood is. Not here. Yeah. Here in teak wood, you can get the E value as 99.7 into 100 Newton per mm square, and you can get all the different permissible stress values directly from here. That is bending stress value is 15.5, then shear stress value is 1, and the perpendicular. And you can see perpendicular compression perpendicular to the grain value is 4.5. So you have to write down all those values and do the same procedure, that is assume the breadth and depth of the beam, calculate the maximum bending moment and shear force, and do the checking for bending, shear, deflection and bearing. Similar question is the fourth one, again the teak wood and with the UD load of 15 kilonewton per meter. So the procedure is quite simple. Assuming the dimensions, calculating the maximum bending moments, doing the check for bending, shear, deflection and bearing. Okay, that's the design of timber beams. Thank you.